Good morning everyone. Here I am going to explain the refraction of light through a lens. So first see what is a lens. A lens is a transparent medium which is bounded by two spherical refracting surfaces. So spherical refracting surfaces means the curved surfaces. Let's see this shape. This is the shape of a glass. Okay, like a carom coin, and it has two surfaces. This is the first surface and this is the second surface, and both the surfaces are plane. These are the refracting surfaces. Why? Because whenever light ray will incident on this surface, the light ray will refract first and enter to the medium, and then after the light ray will incident on the another surface and they will leave the medium, so they will refract once again on the second surface. So we have two refracting surface for this shape, but both the refracting surfaces are plane refracting surfaces. Like you have studied the refraction through a rectangular glass slab, the refraction in a prism when the light ray is incidenting on the plane of the prism. So there we have plane surfaces, but in the case of lens we have the curved surfaces. That means this shape, this surface will be curved inward or curved outward in the case of a lens. So these curved surfaces are called spherical refracting surfaces, and as these are called spherical refracting surfaces, so that means they are the part of a sphere. And if this is a sphere, it has a center and it has a radius of curvature. Okay, and we are just cutting a section of the sphere, and that section be taken as the spherical refracting surface, either from this side or from this side. Now see this shape. Here this plane surface is assumed as this curved surface, correct? So now we have the first refracting surface which is curved inward, and as it is a spherical refracting surface, so that means it is a part of a sphere, so it has a center here. For that sphere we have a center, as because this is a part of a sphere, and we have radius of curvature also. This part is called curvature. Okay, and for that one also, for the another surface of this shape is also we have this inward curved surface, correct? And it is an inward curved surface, so that means here we have the center, we have the radius. Now we are getting a shape which is thin at the midsection and broader at the edges, and as those two refracting surfaces are curved inward, okay, so this is called a concave lens. And now this is, you see, this is a convex lens. Now here we have the outward curved surface. Okay, that means the first refracting surface is curved outside and the second one is also curved outside, and both those surfaces are taken from a sphere, so that's why they have a center. Now you see the symbolic diagram of convex and concave lens is like this. Now if you want to know more about a convex and concave lens, that means the term related to it, see, this is a convex lens and we have the two surfaces. So for this first surface, as it is a spherical refracting surface, so we have imagined a sphere, and for that sphere we have a center. And if for that sphere we have the center here and this is the radius, so we will say this is the center for this surface only, or for this curvature only, and that's why this is called as the center of curvature, and this is the radius of curvature. We have another refracting surface for this same lens, this is the second, and for that we can imagine a sphere, and this is the center of curvature and this is the radius of curvature. Now for the concave lens we can do the same. You see, this is the concave lens, and here this is the first refracting surface, and we have just imagined a sphere for this surface, and this is the center of that imagined sphere, and this is the radius. So we are getting the center of curvature and radius of curvature for this first surface, and this is the second surface. For the second surface we are getting this is the center of curvature and this is the radius of curvature. So for every lens, either it is a concave or convex, we are getting the two centers of curvature and two radius of curvature for its two surfaces, two spherical refracting surfaces. We are getting a new term here, principal axis. So this principal axis means the line joining those two centers of curvature of a lens is called the principal axis. Here also we are getting, see, this is the principal axis, the line joining the centers of curvature of a lens is called the principal axis. So I think you all are clear with these three terms. Center of curvature, you can define the position of center of the sphere whose part is the lens surface. There are two centers of curvature for the two refracting surfaces of a lens. Radius of curvature is the radius of the sphere whose part is the lens surface. So this r means the distance of the center of curvature from the lens. Clear? Now what is the principal axis? You see, it is the line passes from the two centers of curvature of a lens, any kind of lens, either concave or convex. Now how the light ray is incidenting in a lens, you see, and how it is refracting. You see here this is the ray incidenting, and we are taking this ray parallel to the principal axis. So at this point the light ray is incidenting, so we have to draw the normal here. And remember that whenever at any point of this spherical surface, if you are drawing the normal will pass from the center of curvature. In the case of any spherical surface, if you draw the normal will pass from the center of the sphere, and this is the center of curvature we have. Okay, so now we have this one as the normal, and this is the incident ray, and this is the angle of incidence. As the light ray is traveling from this air medium to the glass medium, that is rare to denser, so the light ray will bend toward the normal. So this is the first refracted ray which is traveling inside the material, inside the lens. Okay, now we have second refracting surface here. So the light ray will incident here and it will reflect once again. So we have to draw the normal. This is the normal, and after drawing the normal, what we'll see that as the light ray is leaving the glass, it is traveling from this denser medium to the air medium, that is denser to rare. So the ray will bend away from the normal. You see, this is the normal and this is the ray which is going away from the normal. Okay, so what we are getting, that this is the incident ray which is parallel to the principal axis, and after refraction through a lens, through a convex lens, what we are getting, that the ray which is refracting out from the lens is passing from a specific point, and that specific point which is on the principal axis is called the focus of this lens. So remember that the focus of the convex lens is always on that side. Clear? Now we see the same thing for a concave lens. This is the incident ray parallel to the principal axis, as this is the first spherical refracting surface which is curved inward. So we have to draw the normal like this, and this normal will pass from the center. Now this is the first refracted ray which is bent toward the normal, as the light ray incidenting or entering from this air, that is rare medium, to this glass which is denser medium. So the light ray will bend toward the normal. Now the refraction occur here at the second point also. So here we have drawn the normal, and see what we are getting. This is the direction of the ray which is incidenting at this point, and the ray which is leaving that medium, this has the direction toward that side. Now here what we are getting, in the case of convex lens, the parallel ray which is incidenting on the lens, it is converges and it is coming toward the principal axis. But in the case of concave lens, again this is the parallel ray, but it is diverging from the principal axis, it is going away from the principal axis. So every concave lens has a diverging nature, and every convex lens has a converging nature. They will converge the rays at any point, and here these concave lenses diverge the rays. But here, as this is the direction of the ray which is coming out from the lens, from this concave lens after refraction, so what will be the direction? How will predict the direction of this emergent ray? So for that we will see a point here. That means as this ray is going to that side, so we will predict that what is the position from where the ray is coming. Okay, so we'll predict the position on this principal axis, and that point, that specific point is called the focus of this concave lens. So remember that the focus of a concave lens is always on this side, or always on the left side. Okay, so in the ray diagram you have this idea that focus of a convex lens is always on that side, and for a concave lens the focus is always on this left side. Clear? And this focus gives the direction of the ray which is going out after refraction from a concave lens. Clear? Now you see this one. To know more about this focus, we are taking the two parallel rays incidenting on the convex lens, and as you have the idea, we are not showing the internal refraction here. Okay, we are just drawing this this ray which is incidenting on the lens, and the ray which is passing from the lens, okay, which is getting out from the lens. So here we have, this is the ray which is incidenting on the lens, and this is the ray which is refracting out from the lens. As we have the idea, it will pass from the focus. Here again we are taking the parallel ray, it will pass from the focus. Now this focus is a special point, and the distance of this focus point from the lens is taken as the focal length, okay. And for the convex lens, the focus point is here always. Now you see, if we are uh, recalling the principle of reversibility, so if the ray is reversing back, so it will take the same path. Suppose we are assuming that the rays are coming from focus, then it will incident on the lens and it will go take the same path. Now see this one, we have imagined the same, the ray is incidenting from the focal focus, okay, and it is entering to the lens, it is incidenting on the lens, on the convex lens, and they will refracting out from the lens and taking a direction parallel to the principal axis, correct. So now we are getting the 2 point on the either side of the lens, okay. So this is the first focal point from where the rays are entering to the incidenting on the lens, and they are refracting parallel to the principal axis. And the second focal point is this one, when the rays incidenting on the lens, on the convex lens, they are directed to a particular specific point. That point is called second focal point, okay. And this is the second focal point is the actual focus of a convex lens. Whenever we'll take the focus of a convex lens, we'll take this one, the second one, okay. The second focal point we'll consider. Now the focal length means the distance from the lens to that focal points, okay. So this is the first focal length and this is the second focal length, this distance I'm telling, okay. Now is for the this is for the concave lens. You see, this is the parallel ray incidenting here, and as you have the idea, if it is a concave lens, the rays will diverge, it will go away from the principal axis with that means in a direction such that they are appearing from the focal point, from the focus of a concave lens. So this is the actual focus of a concave lens, clear. This is the another parallel ray incidenting on the lens, and see, this is the direction of the ray going out from the lens, QS, okay. And you see this QS, the direction of the QS is taken from the F, from the focus of this concave lens, clear. And this is what we call the focal length. Now see, again we are recalling the principle of reversibility. That means if the light ray is incidenting on a concave lens such that they are directed to coming to the focus, let's see, here we are taking this, see, this is the incident ray right now we are taking, and this is incidenting on the lens such that it is directed to the focus of the concave lens, okay. So after refraction, these ray will pass parallel to the principal axis, as you see, correct. So we are getting again two focal point for a concave lens. This is the first focal point, okay. First focal point means the light ray are coming and incidenting on the lens such that they are directed to the point. That point is called first focal point, and after refraction the rays will take a direction parallel to the principal axis. So we can define the first focal point, and this is the second focal point. This is the second focal point. That means if the rays incident parallelly on a concave lens, then the ray takes a path after refraction such that they are appearing from a special point on the principal axis. That point is called the first focal point, sorry, the second focal point, and this is the actual focus of this concave lens. Second focal point is the actual focus of a concave lens. As I told you that whenever we are taking a concave lens, focus will be always on this left side. For the concave lens, for the convex lens, we have the focus on this side, on the right side, clear. So we got the first, see, this is the first and this is the second focal point for a concave lens, and this is the first focal length and this is the second focal length. So these principal foci, so these things are clear. First focal length, second focal length, I mean first focal point, second focal point, and first focal length, second focal length. Now see this one, optical center. So there is a significance of the point at the midpoint of the lens, at the mid section of the lens. What is the significance? That whenever the light ray is incidenting on a lens such that it is directed to the special point at the mid of the lens, then the light ray will refract inside the lens, and they will take, after refraction, they will take a path. Okay, they will take a path which is same as the direction of the incident ray. Correct. Here also you can see this is the ray incidenting on the lens, and after refraction it will take the same path. So it is just like the refraction occur in the case of rectangular glass ray. See, we can see there is a lateral shift of those two. See, this is the incident ray, this is the direction of the incident ray, and this is the emergent ray, and there is a lateral shift. So what we will see, what we will say here, that the ray is not changing its direction, it is not deviating. So if the lens, if this lens is very much thin, then what we'll see, we will see, we will take this lateral shift is very less. Okay, almost negligible. So here we will draw like this. This is the ray incidenting, and this is the ray, this is the ray incidenting on the lens directed to the point, and it is the emergent ray from the lens. So what we'll find, what we'll find that this ray is passing undeviated through the lens. And here also, in the case of concave lens also, this ray is passing through the lens and remain undeviated. Clear? So optical center is the position if the ray, any ray is incidenting which is directed to the optical center of a lens, the ray will pass from the lens without any deviation. Clear? And this is the significance of optical center of a lens, and this is how we can define the optical center of a lens. Clear? Now if we take more than one ray and all the rays are parallel, you see this is the ray passing from the optical center, remain undeviated, and the other rays are parallel to this ray. Okay, so here these parallel rays are actually the rays which are coming from any object which is taken at infinity. Okay, an infinite object will send the parallel rays. So you see the parallel rays are incidenting on a convex lens here. Okay, and as the convex lens has a converging nature, that means the ray will bend toward the principal focus, toward the principal axis. Okay, so here this is the ray which is bent toward that side after refraction. Okay, so all the rays, all the parallel rays incidenting on the lens, you see all the rays will meeting at a particular point. Clear? So that point gives a real image of the infinite object from where the rays are coming. Clear? And that position will be here, and the dotted line I have given you, this is called the focal plane of the lens, and that focal plane is the perpendicular, a plane which is perpendicular to the focus. Clear? Just try to understand. Here see, again I have taken here, like I have taken the parallel rays, here also I have taken the parallel rays, you see. Okay, this is the ray passing from the optical center. So after refraction through the lens, this parallel ray is converging at a particular point, and this point is again on this plane, and that plane is called focal plane. So here this particular plane is a plane which is perpendicular to the focus of this lens. Okay, and if obliquely from any direction rays are incidenting on the convex lens, all the rays will converge at a point, and all those points belongs to this focal plane. Clear? So that means here any direction, from any direction, if the parallel rays incidenting, will get the point on this plane only. Okay, and that point is actually the image, the real image of that infinite object. Clear? Now in the case of concave lens, you see here it has the diverging nature, so the parallel rays incidenting, see this is the ray passing from the optical center, remain undeviated, but the other rays, other parallel rays incidenting, and they are diverging. You see this is, so they will not meet at anywhere. But if we see from this side, if we see from this side, these rays are coming. So from where these rays are coming, so to predict the position from where these rays are coming, we will produce this ray backward, and we will find a point here, and that point gives the virtual image of that infinite object from where these rays are coming. Okay, and that position of this image, this virtual image, will be on the focal plane of this concave lens. Clear? Here why we have produced the line backward, because from this side when we will see, we will find that some rays are coming, but what will be the source of those rays? So to predict the source, to predict the direction of those rays, will produce the line backward. And now from here we are assuming that this is the position from where the rays are coming. This is the position which act as the source of these rays. This is the position which sent these rays. This position is appeared in such a way that this point is sending the rays, if we are seeing from that section. Okay, and this is called the virtual image. Why it is called the virtual image? Because the rays are actually not meeting here. In that case, the rays, the refracted rays, are actually meeting at this point. So if they are actually meeting at this point, we'll put a screen here and we'll get an image that is called the real image. But here in that case we won't get any real image, because if we'll put any screen here, then we'll not get, because rays are actually not meeting. So we have to just produce backward these rays. So then we'll get a point here, and inside the lens, from this side inside the lens, we'll get a image of this infinite object, which is the virtual image. And that point of the virtual image belongs to the focal plane. You see here also we are taking the different direction. Here these are the three parallel rays incidenting on the concave lens, and see, this is diverging to that side. We have produced the line backward. Here also we have produced the line backward. So this is the position of the image of the infinite object from where the light rays are coming, and this points belongs to this focal plane. Okay, so this is the plane which is perpendicular to the point, to the second focal point, correct, which is perpendicular to the focus of this lens. So now we have two focal plane. You can see we have the first focal plane for a lens, and we have the second focal plane for a lens, as because we have two focal points, first and second, correct. So this is all. Thank you.